Welcome to the Cosmic Timeline, our universe's epic journey. Here, we'll travel through billions of years, starting from the universe's explosive birth and following its evolution across time. Prepare to explore key events that shaped galaxies, stars, and even our own planet Earth. Our journey begins with an incredibly dense point known as the singularity, so packed with energy that it's almost beyond imagination. In a tiny fraction of a second, this singularity unleashed an event we call the Big Bang, causing rapid expansion. The universe went from smaller than an atom to enormous in less time than it takes to blink. As it expanded, temperatures began to drop, allowing energy to convert into the very first particles. These tiny bits of matter would eventually form everything from atoms and stars to entire galaxies. Right after the Big Bang, the universe went through a period called inflation, where it underwent exponential growth, expanding faster than the speed of light. This may sound impossible, but this rapid stretching of space itself doesn't break the rules of physics in the usual sense. During inflation, most tiny bumps or wrinkles evened out in a smoothing effect, although some slight differences, called quantum fluctuations, remained. Over billions of years, these subtle variations grew into stars, galaxies, and clusters, making them the true seeds of structure in our cosmos. In the early universe, extreme temperatures created a state called the quark-gluon plasma, where quarks and gluons swirled freely. It was so hot and dense that stable particles simply couldn't form. But as the universe continued to cool, quarks began to stick together, resulting in the birth of protons and neutrons. Soon, these particles underwent a process known as nucleosynthesis, merging to form the first light elements, primarily hydrogen and helium. These elements would become the raw materials for the first generation of stars. As time went on, some areas in the early universe were slightly denser than others, leading to gravitational collapse. These regions pulled in surrounding gas and dust. Under immense pressure, the gas heated up, allowing the first stars to ignite. These stars, often called population 3 stars, were massive and burned their fuel quickly, but they paved the way for future stellar generations. Over time, stars clustered together, forming protogalaxies. Through further merging and growth, these protogalaxies evolved into the diverse galaxies we recognize today, from graceful spirals to giant ellipticals. One of the most fascinating clues about our cosmic origins is the cosmic microwave background, CMB. This faint glow fills the entire sky and is often referred to as the afterglow of the Big Bang. If we could see microwaves with our eyes, the sky would look like a glowing backdrop. The CMB is nearly the same temperature everywhere, showing how uniform the early universe was, though careful measurements revealed tiny fluctuations. By studying these slight differences, scientists glean vital insight into the early universe's conditions, including how matter began to clump together to form stars and galaxies. Galaxies don't remain static, they grow, collide, and reshape themselves over time. In these mergers and interactions, galaxies can morph from spiral shapes to elliptical ones, or even trigger bursts of new star formation. Within these galactic environments, star formation continues across cosmic history, creating waves of new stars of varying sizes and lifespans. As these stars age, they forge heavier elements through nuclear fusion. When massive stars explode as supernovae, they scatter these heavier elements into space, enriching future generations of stars and planets with the building blocks for everything from rocky worlds to living organisms. Despite our progress in understanding the cosmos, a huge chunk of it remains mysterious. Scientists believe dark matter acts like an invisible glue that helps hold galaxies together, preventing them from flying apart as they spin. On the other hand, dark energy seems to be pushing galaxies apart at an accelerating pace, driving the expansion of the universe faster and faster. Because these components are of unknown composition, they represent some of the biggest unsolved puzzles in astrophysics, making up the vast majority of all that exists. In this grand tapestry, our planet Earth is just a tiny sphere orbiting a star we call the Sun. Together with a family of planets, moons, and asteroids, we form the solar system. This system is one of billions within the Milky Way galaxy, which itself is part of a neighborhood of galaxies referred to as the local group. Beyond that, the local group resides in an even larger cosmic web filled with galaxy clusters, filaments, and voids, all woven into the universe. Recognizing how we fit into these vast structures underscores the remarkable story of how we came to be. Today, we estimate the universe's age at around 13.8 billion years, and we measure its expansion rate, the Hubble constant, at roughly 73 kilometers per second per megaparsec, meaning galaxies move away from each other faster the farther apart they are. Observations also suggest a flat, overall geometry, denoted by omega equals 1, implying that the universe will likely keep expanding indefinitely. As time goes on, galaxies will drift farther apart, and the night sky will look different to any future observers. While we don't know every detail about the universe's ultimate fate, it's clear that our cosmic story is still unfolding, and we are part of it.